Hello, everyone. Thank you for being here today. My name is Kamal, and I'm here with Andrew. We are both from the Kennesaw State University. I will talk about machine learning and cybersecurity analytics using NSL-KDD dataset. After my part, Andrew will present his topic, Model Inversion Attack with HPCC System. I'm a master's student at Kennesaw State University, major in software engineering. I'm working as a graduate research assistant under Assistant Professor Mr. Saidaman Puri. My goal here is to demonstrate how HPC system can apply it for security protection. For my experiment, I have used the NSL-KDD dataset. This presentation will help to show how an open source platform can be used for the intrusion detection system, leveraging the parallel computing power of the HPC system. This open source platform also helps an organization to save cost without compromising the performance required for an enterprise level intrusion detection system. Before I get into the machine learning algorithms and dataset detail, first we need to understand what is an IDS and how HPC system can play a crucial role here. An IDS is a software or combination of application and hardware devices that monitor network traffic to detect known threats or suspicious or malicious activities. An intrusion refers to any unauthorized attempt to access a computer system, including workstation, server, firewalls, or even the IDS itself. This network architecture shows possible positioning for placing an IDS, which can be a host-based or network-based. While a firewall uses a rule to prevent the intrusion by deciding whether a packet should be forwarded to the internal traffic, an intrusion detection system detects the packet that shouldn't pass the firewall. And from the input from the IDS input, the intrusion response can adjust the firewall rules or shut down the computer. There are two types of intrusion detection. One is signature-based and another is anomaly-based. A signature-based anomaly detection is detect the system, identifies attack by matching them to known patterns or signatures stored in the database. It compares network data against those signatures, producing very false positive alerts. However, it only detects the threads that matches the predefined signatures and may fail to detect new or modified attacks. NSL-KDD dataset, and basically now the anomaly-based intrusion detection, in the other hand, it used a statistical analysis to spot the deviation from the normal behavior and helps an IDS to detect an unknown or new threats. But it may produce more false positive alerts compared to signature-based intrusion detection system. Our analysis is based on the anomaly-based intrusion detection system. NSL-KDD dataset. The KDD Cup was an international competition focused on knowledge discovery and data mining tools. It collected a large data of internet traffic records known as KDD99. The NSL-KDD dataset is a refined version of the KDD99 created by the University of New Brunswick in Canada. So NSL-KDD stands for Network Security Laboratory, Knowledge Discovery, and Data Mining. The NSL-KDD dataset includes the following attacks: the denial of service or DDoS. DDoS floods the system with abnormal traffic and causing the shutdown or disruption. And probe involves gathering information without breaking the system. Then user to root or U to R start start as a regular user and get control to the root access. And remote to local or R2L gains local access to a machine from a remote location. NSL-KDD dataset has 43 features, and original NS-KDD Cup 99 has the 42 features. The dataset is publicly available in CSV format. There are around 125,000 records in the train dataset and around 22,000 records in the test dataset. Train dataset has normal records of around 67,000 and network attack records are around 58,000. In the test dataset, it has around 9,000 normal records and around 12,000 attack records. We can say it is a balanced dataset. As we know, a balanced dataset is the one that contains the equal or almost equal number of samples for positive and negative classes. Out of 43 features, there's a column called attack, which is the target or independent variable in the classification algorithm. It has 16 distinct attacks. Normal attack is denoted as 0, and the other attack types are denoted as 1. Machine learning model development steps that I have used. The first step was dataset selection. I had selected the NSL-KDD dataset, which was our target domain, cybersecurity. I ensured that it contains the necessary features for the model to learn effectively. And then second step is data processing. I have cleaned and preprocessed data, including handling missing values, normalize the features, and split the data into training and test dataset. The third step was model selection and training. I have selected all the classification algorithm available in the HPCC System machine learning library. The last step was the evaluation and comparison. I have evaluated the model accuracy and compared the result against a baseline model to assess the improvement. And technology stack, we have used the ECL programming language and embedded Python in HPC system platform. Embedded Python is required for the GNN bundle to access the Keras and TensorFlow library. This is the reference paper used to establish the baseline for our analyzed result. The paper is published in 2021 International Conference on Technologies and Applications of Artificial Intelligence. The title of the paper is Machine Learning in Cybersecurity Analytics Using NSL-KDD Dataset. Machine learning in HPC system. The HPC system machine learning library offers a diverse set of algorithms accessible through ECL programming language and optimized to leverage the parallel computing power of HPC system. The library includes several core bundles that support various machine learning activities. Also, it has a dedicated bundle for different algorithm families. HPC System Machine Learning Library has several machine learning bundles, both supervised and unsupervised. I have used only the supervised and classification algorithm. Logistic regression, generalized linear model, support vector machines, learning tree, and generalized neural networks are used for this analysis. Each algorithm provides a set of common methods. Get methods, prediction or classification, and assessment. So get model allows the algorithm to learn from the provided training data and return the model. The generated model encapsulates the learning and can be used for predicting value and classify new data. Each bundle is offered method to evaluate the predictive power of the learned model and tailored for a specific algorithm. The married interface enables the execution of multiple similar actions in different datasets with a single invocation. By triggering multiple activities simultaneously, it fully leverages the parallel processing capabilities of HPC system clusters. It allows all activities to execute in one pass. Running these activities in parallel distribute the workload across all the nodes in the cluster that helps optimizing the performance and minimizing the runtime. Preprocessing. Preprocessing is an integral part of machine learning core bundle. It provides essential function for data preparation. Key preprocessing activities include label encoder, standard scaler, and one-hot encoder. Label encoder transforms categorical values into numerical format that allows the use of categorical feature for the machine learning algorithm. Standard scaler standardizes data by adjusting to have a mean of 0 and standard deviation of 1.0. It ensures uniformity in the data range. And one-hot encoding covers specified categorical features into binary absent or present value that allows algorithm to process categorical data more effectively. For label encoding, at first we need to identify the categorical features. From this categorical feature, we will get a key, and using getKey method, then the key is used to encode the data into numerical format by using the encode method. So you can see that the categorical value is converted to the numerical value. If you want to use without label encoding, we need to do this manually using if-else condition, which can produce error, and it also need to update the code for every new data. Split method divides the data into train and test based on the split ratio value. Here, split ratio 0.8 means 80% train data and 20% test data. It's possible to shuffle data if needed by changing the shuffle parameter to true. Standard scalers scale the data to ensure that each feature is on the same scale. Standard scale object is initialized with the train data, and then scale method scale the data. So you can see that the data is scaled with this after this function. One-hot encoder creates object with dataset containing specified feature. It contains a dataset that has the specified feature that we want to apply the one-hot encoding. And then encode method do the encoding. And after one-hot encoding, we need to append that with the original data. Learning tree bundle. Learning tree bundle supports the decision tree, random forest, gradient boosted forest algorithm. These algorithms are conceptually simple and easy to understand and interpret. Decision tree is one of the oldest algorithms which is using at least since 1930. I have got 99% model accuracy using this classification forest algorithm. These are the hyperparameter used to control the learning process. Adjusting the max depth of the tree of the forest can get the advantage of the different algorithm families. The default parameter works for my analysis. Here is an example on how it divides the record into 3 parts using mirrored interface. I have added one field in the dataset called VID, and then I divide the dataset into 3 parts with 3 different VID values. And 2 field has a parameter called V field where we need to pass the VID. If we want to use the mirrored interface, then we have to use the VID values. And if we don't want to use the mirrored interface, then we can skip the V field. Rest of the parallel processing is done by the other methods in this algorithm. Logistic regression bundle. Logistic regression is a supervised learning algorithm. It uses the logistic function to predict the probability of a binary outcome. The name of the algorithm is somehow misleading. The logistic regression is a classification algorithm. So I have got 96% model accuracy from this trained model. These are the hyperparameters used to control the binomial classification process. The default parameter works well in my analysis. Support vector machine. Support vector machine is one of the popular supervised classification algorithm. The main goal of SVM is to find the optimal hyperplane that separates the data point in different classes. I have got 97% model accuracy, which is slightly lower than our baseline result. These are the hyperparameter used to control the SVM classification process. The default kernel type was RBF. I have used linear kernel for the kernel type. Generalized linear model or GLM bundle. Generalized linear model with the binomial classification algorithm. GLM models allow us to build a linear relationship between dependent variable and independent variable, even though their underlying relationship is not linear. I have got 95% model accuracy using this algorithm, and our baseline result doesn't have the GLM algorithm. These are the hyperparameter used to control the classification process for the GLM bundle. I have changed the FAM value to binomial for the classification process and adjust the max iteration for the classification for the better accuracy. Generalized neural network or GNN bundle. Generalized neural network has interface to Keras or TensorFlow supporting neural network for processing multimedia data such as image, video, and time series data. I have got 97% model accuracy using GNN bundle. GNN has the following hyperparameter. All the parameters are altered during the experiment. Selecting the right batch size and number of epoch is very important for this algorithm to have the better accuracy. This is the comparison of our analyzed result. Classification first algorithm using linear learning tree bundle has the highest accuracy among all 5 bundles I have used. GLM has the lower accuracy compared with other bundles, but we have got more than 95% accuracy for all the algorithms. Maximizing the accuracy of machine learning models requires understanding their specific assumption and constraints. It also demands expertise in data science and statistics. So it is very important to consult with expert before exploring any machine learning model for any dataset or making any claims. That's all from my side. Thank you, everyone. Now, now it's turn to Andrew. Thank you.
Thank you, Kamal. Hello, everyone. My name is Andrew Polisetti. I am currently pursuing my master's degree in computer science at Kennesaw State University, where I work as a research assistant under Professor Dr. Yongxi. Today, I will be discussing an important and emerging threat in the field of machine learning, model inversion attacks, or MIA. Specifically, I'll be explaining how these attacks work, why they are significant, and the various methods we are employing to prevent them using the HPCC Systems platform, leveraging ECL language. The goal of this presentation is to provide you with a comprehensive understanding of MIA, highlight the vulnerabilities in machine learning models, and discuss our approach to securing these models in critical sectors like finance. What is model inversion attack? Next. Model inversion attacks represent a significant security threat in machine learning. In these attacks, adversaries exploit the prediction outputs of a machine learning model to reverse engineer and reconstruct sensitive input data. For example, if a machine learning model is used to predict credit risk based on personal financial data, an attacker could potentially reconstruct this data, gaining unauthorized access to sensitive information like income, credit scores, or loan amounts. MIA is particularly dangerous because it can lead to severe consequences, such as identity theft, fraud, and compromised decision-making processes. These attacks can expose vulnerabilities in models that are thought to be secure, especially in sectors where data privacy is paramount, such as healthcare, finance, and government. In essence, while machine learning models are powerful tools for prediction, they can also become targets for attackers if not properly secured. Now, let's talk about the methodology of our project. Methodology. To investigate and counterattack model inversion attacks, we employed a systematic approach using the HPCC Systems platform. Our methodology started with acquiring a dataset, specifically a loan dataset that contains personal details of individuals who have taken loans. We first prepped the data, which involved cleaning and transforming it to ensure that it was suitable for machine learning tasks. Next, we preprocessed the data which included handling missing values to improve the model's performance and accuracy. Using the HPCC Systems machine learning bundle, we developed three distinct models: the original model, the attack model, and the prevention model. The original model was built to predict whether a loan applicant would default on their loan. The attack model was designed to simulate a scenario where an attacker tries to reconstruct the sensitive data using outputs from the original model. Finally, the prevention model was developed to mitigate the attack by introducing defensive mechanisms such as adding noise to the data. Dataset. Dataset used. The dataset we use is commonly known as the loan dataset, and it comprises detailed information on individuals who have taken out loans. The datasets includes 151 features. Though not all of these features were used in our models, key features include ID, loan amount, loan term, interest rate, and other financial indicators. For the original model, we focused on selecting few features that were most relevant for predicting loan details. These features were carefully chosen based on their predictive power and relevance to the target variable, which in this case is the loan status. This dataset serves as a robust foundation for modeling credit risk, as it includes both quantitative and qualitative information that can influence a borrower's likelihood of defaulting. By using this dataset, we were able to create a model that predicts loan defaults with a significant degree of accuracy, but also one that is prone to model inversion attacks, which is what we aim to address in our research. Let's see the record sets we used. Record set used. For experiments, we developed models using both learning trees as well as logistic regression, which are available in the HPCC Systems machine learning bundle. In the learning trees model, we used four specific features: loan amount, annual income, depth for income ratio, and loan status. These status were selected for their simplicity and a direct impact on loan approval decisions. However, for logistic regression, which is a more sophisticated and interpretable model, we expanded our feature set to 6 features, adding FICO credit score and interest rate to the mix. Now let's see what is independent and dependent features are. Independent features such as loan amount, interest rate, FICO score, annual income, and DTI are crucial as they serve as the predictors for our model. And the dependent feature is the loan status, which indicates whether a loan was approved or not. This binary outcome is what the model aims to predict. The train and test dataset. As you can see here in the graph, to train and evaluate our models, we split the data into training and testing sets. From the graphs, we see that for both original model and attack model, we have taken same amount of train data and test data. The training data consisted of 80,000 records, which we used to fit the models. This allowed the models to learn from a broad range of examples, capturing the underlying patterns in the data. For test data, we considered 40,000 records to evaluate the model's performance. By keeping this data separate from the training set, we were able to assess how well the model generalized the new unseen data. For the attack model, we also used predicted outputs from the original model as inputs. This approach simulates a real world scenario where an attacker would have access to the model's predictions and could use them to infer sensitive information. The train test split is a critical part of our methodology, ensuring that our results are both valid and reliable. Coming to the models, we developed three key models to explore the effects of model inversion attacks and potential prevention strategies. The original model was designed for credit risk assessment. It used features like loan amount, interest rate, and FICO score to predict whether an individual would default on their loan. The attack model was then developed to simulate an opposing scenario. This model was trained on the outputs of the original model and additional test data, allowing it to mimic the predictions and potentially reverse engineer sensitive information. Finally, the prevention model was designed to protect against such attacks. In this model, we introduce noise by flipping the binary outputs of the top 30% of predictions, making it harder for an attacker to accurately infer the underlying data. This is the flowchart for the original model. First, we train the model by giving the training data and test the model with the testing data, from which we get the predictions, that is the output. But for the attack model, this is the flow. Next, please. This is the flowchart for the attack model. We give the training data as well as the predicted data from the original model and test the model with the testing data. Each of these models plays a crucial role in our research, offering insights in both the vulnerabilities and potential defenses in machine learning systems. Next comes the learning trees. The learning trees bundle in HPCC systems is a collection of tools and algorithms that help you create and use machine learning models. It includes three based methods that are commonly used for tasks like classifying data, predicting outcomes, and more, all within the HPCC Systems platform. This is the code, and the first is mapping the loan status values to numbers. The values are fully paid, current, and charged off. We map them to 1, 2, and 3. Next is prepping and preprocessing the data. First, we sorted the data. Then, clean the data by removing all the null values from the dataset. And then divided the data into train and test data for both original model as well as the attack model. Next, we divided the independent and dependent variables. For the prediction, we took the classification forest bundle, which is the learning trees bundle, and gave both the independent and dependent features and trained it. Then we tested the model with the testing data. Attack model. The attack model code is similar to original model, but instead of the dependent variables, we give the predicted output of the original model for training. Prevention model. For the prevention model, we added noise to the top 30% of the data. The code explains how we transform this data. Initially, we used learning trees for our modeling. The learning trees model achieved a raw accuracy of 72%. While this accuracy was acceptable, we identified areas for improvement, particularly in handling complex relationship between features. The logistic regression. The logistic regression bundle in HPCC systems offers tools to easily create and use logistic regression models. Logistic regression is a popular method used to predict whether something will happen, like yes or no, based on other related information. This bundle makes it simple to build and run these models on the HPCC Systems platform. To enhance performance, we transitioned to logistic regression, a more robust and interpretable method. Similar to the learning trees bundle and the code we implemented over there, in logistic regression, the values are fully paid, current, and charged off. But we map them to 0, 0, and 1 because logistic regression accepts only binary values, that is 1 and 0. Next, prepping and pre-processing the data. First, we sorted the data, then cleaned the data by removing the null values, then divided the data into train and test data for both the original model and the attack model. Next, we divided the independent and dependent variables. For the prediction, we took the binomial logistic regression bundle, which is the logistic regression bundle, and gave both the independent and dependent features and trained it. Then we tested the model with the testing data. Attack model. The attack model code is similar to the original model, but instead of the dependent variables, we give the predictor output of the original model for training. And this is the code for the attack model. And next, it's the prevention model. For the prevention model, we added noise to the top 30% of the data. The code explains how we transform the data. We just flipped the zeros to ones and ones to zero just to confuse the attacker. Next, the logistic regression model improved the accuracy to 86%, demonstrating a significant improvement over learning trees. However, when we tested the attack model, it achieved an accuracy of 85%. This close performance to the original model highlighted a vulnerability, as the attack model was nearly as effective at predicting outcomes. These results underscore the need for effective prevention strategies, as even small gaps in security can be exploited by adversarial models. To counter the identified vulnerabilities, we implemented a prevention model by introducing noise into the prediction outcomes. Especially, we intentionally flipped the binary prediction outcomes for the top 30% of the data. This strategy aimed to confuse the attack model by providing misleading information, thereby reducing its ability to accurately infer the original data. As expected, this approach reduced the model's overall accuracy to 64%. While this represents a decline in performance, it is a trade-off for enhanced security. The prevention model effectively impaired the attack's ability to exploit the system, making it a viable solution for protecting sensitive data in machine learning applications. Our ongoing research will focus on refining this model to balance the trade-off between security and accuracy, potentially exploring other noise-adding techniques or multi-layered defense mechanisms. Accuracies. These are the graphs showcasing the accuracies of each model in both learning trees and logistic regression. For original model, learning trees have 72% of accuracy and logistic regression have 86% of accuracy. For the attack model, learning trees have 69% of accuracy and logistic regression have 85% of accuracy. For the prevention model, learning trees have 59% and logistic regression have 64%. Conclusion. In conclusion, our research highlights the importance of securing machine learning models against model inversion attacks, which pose a significant risk to data privacy. Our prevention model, while effective, demonstrate the inherent trade-offs between accuracy and security. This finding undergoes the need for further research to develop more sophisticated defenses that can protect sensitive data without compromising model performance. Moving forward, we plan to explore additional prevention techniques such as access control and output restriction to enhance our model's robustness against attacks. We also intend to expand our research to cover other types of machine learning models and data sets, broadening the applicability of our findings and ensuring that the solutions we developed are generalizable across different domains. Ultimately, our goal is to contribute to the development of secure, trustworthy AI systems that can be confidently deployed in critical applications where data privacy is of paramount importance. I would like to express my sincere gratitude to HPCC Systems for providing the tools and resources that made this research possible. I would also like to extend a special thanks to my professor, Dr. Yongshi, for his invaluable guidance and support throughout this project. And thank you, everyone.